James Sykes, CEO and President, Baselode Energy Corp. Last Monday, August 9th, we released news release detailing radiometric results from an airborne survey. We really want to follow up with that and show you, the investors, and anybody else interested in the company, how we come up with drill targeting and why we're very excited about Hook. So let's dive into it. Here we are with the disclaimer. You can read at your own leisure at a different time. YouTube channel, please watch our YouTube channel if you're not familiar with some of the companies or what we've done in the past as Baselode. Very exciting stuff, very interesting. You can learn a lot about our projects and methodology. Hook project, where we are, eastern side of the Athabasca Basin, just outside the edge, highlighted in that red box. Looking for these Athabasca 2.0 style projects, high-grade uranium, basement hosted, right near surface, open pitable. That's what we want to find. How are we going to find these? Well, we got to pick the right projects, and we think Hook is definitely the right project. There's a lot of excitement that can be said for Hook. So it was born of an idea of three factors, really. One being this maglow. For the untrained eye, is not entirely sure if you can see that northwest maglow feature between McCarthy River and the Hook project, running northwest, kind of like that. And then it hooks south, right where our project is, and leads to another high grade showing Zone S Hook Lake, which is just south of our project, on trend though with the project itself. Does this magnetic glow feature have anything to do with high-grade mineralization at all? Not entirely sure. It's a wild idea. It's huge. It's large, 75 kilometers, something like that would draw in water, draw in fluids. That our Hook project, great location. And then also for the Zone S Hook Lake area, our director, Mr. Charles Beaudry, he worked in the area, 1970s, late 1970s, early 80s. He was part of the first drill team up there. He mapped it. We'll see one of these maps coming up later on. So we've already had an understanding of the area, but also what was, I guess the idea of mineralization without pursuing graphitic rocks. And so these just pure structural hosts. With the radiometrics that we did, this news release, we're going to try and show how we're going to target these things. It's done slightly different than following up on EM. So right now we're looking at the surface results because we want to get to a near surface deposit as quick as possible. We think that's the most logical way forward. The less you have to dig, the better. If you can find something near surface, then great. That's the best way to start. So this is where we start off with this broadcast here. What the results really mean. And this was an airborne survey, so we had a plane flying along the treetops, and it's got these big crystals picking up radiation, and it can pick out where all of these anomalies basically are. And then you just rank them based on uranium values and total count values. You come up with a pretty simple system: high priority, lower priority. So the more red that you see, potentially the higher uranium. And then you're looking for clusters of these things. And so you can see the highs here. There's at least 5 nice areas of highs. But then once you start to circle these areas and cluster them, then you start to really build up these targets. So this provides our main priority for where we want to put the drill. Because again, we want to find something near surface that would be mineable, something that could come out of the ground pretty quickly. So this is definitely one of the easiest ways to do that. But when you're exploring with radiometrics, it is really a limited tool to pushing down deep. I'm talking, you can only go about a meter deep with radiometrics before you see the bedrock. So there's a lot of unknowns that happen there. So a lot of those anomalies that we're looking at, they could be boulders, they could be glacial drift, they could be outcrops with uranium veins. There's a lot of possibility. When you look at northern Saskatchewan, this is the terrain out there. There's not outcrop everywhere. It's not like you're walking on the mountains and you expect to find all of these anomalies everywhere. You're lucky to see through this vegetation, and that's with a radiometric survey. Other magnetic forms, you can definitely go deeper. You can start to see how vegetation forms on some of these outcrops as well. It's difficult to see beneath the rocks here. So again, we're just looking at the surface, 1 meter from the surface down to about a meter. That's what we think we're picking up. Are they outcrops? Are they boulders? Field crews out there. They're out there right now. They went up there in earlier July, but now they're back to follow up some of these outcrops. The goal and idea is always, again, you're looking for something near surface. Nice high grade deposit. But to be very honest, that would not occur anymore. Those would have been found very early on. So what if you still have some that are hidden a little bit more within the muskeg, just covered? What if they're down 5 meters? Radiometric survey will not pick that up. What if they're still not even just within the muskeg? What if they're still buried within the rocks? Something like what we see here, that you're not going to get a shadow of glaciation affecting anything with those deposits because they haven't been reached, they haven't been touched, they haven't been scoured yet. So there is that possibility. What we've done is we've taken two of the areas that we kind of like with other geophysics and made those our priority targets right now. South Geikie, which incorporates target areas 1 and 2 because of those massive radiometric anomalies, great place to really focus on, nice trend of things. And then the Beckett area as well. And that's looks like a small trend of lower priority, but Beckett is really based on geophysics. And this was one of Cameron's original, this was Cameron's place that he wanted to go to right away. It drew him right there. The structure looked great. And as we've gone through putting everything together, there's without a shadow of a doubt that is a great looking target. So Beckett's absolutely wonderful, and we're hoping to emphasize that fact as we keep going through this. So we want to see beneath the surface. You need geophysics to do that. And part of the survey that we flew was a magnetic survey. You can see a lot of lines here. You can see a whole bunch of different colors, and this helps us see beneath the surface. Now we can start compiling subsurface information with what we are seeing at the surface, and it all helps us understand. You'll see a few of these features here, northwest anomalies. These are all artifacts. These are not real. This is preliminary data, so I caution everybody about looking at this, but the resolution is so high, the detail was so high in this survey that it really doesn't need post-processing. It's pretty phenomenal. With the final data, yes, those lines would be removed. So they're artifacts. You'll see them through some of these images. Just ignore them. You just got to get used to ignoring them. You start drawing these lines, and that's what you can see with the magnetics. You start drawing these lines. I've colored them in blue. I've got a thick blue one there and a thick purple one. We'll talk about that. What a lithology is, it's basically your different rock units and how they're lined up. The thick blue line, you can follow this line all the way from the 50 kilometers, 100 kilometers north, 50 kilometers, 100 kilometers south. There's mineralization along that trend. It has an interesting kind of potential origin for this area. That purple rock, the purple line that you can see there, we're calling that a mafic unit, a mixed mafic and granite unit. So when we can follow that line just along this edge between the two differing magnetic signals, we can follow that down to the S zone, the high grade zone down there. When we cut out and look at the regional magnetics, so the data that is available from the Saskatchewan Geological Survey online, this is what you're looking at. You can see that the magnetic trend is pretty well similar. So we've got good confidence in what we see down there. Once you take off the magnetics and you start looking at the lines that were just drawn, you can see different areas of shapes. You can see a thick black line that really separates two structural styles going on at Hook. You got an intensely folded area to the northwest. Between the black line and that blue line is a moderately to weakly folded area. You can start to see these little folds show up. And then beyond to the southeast of that blue line, you're seeing these rocks that are completely linear, not folded really. If they're folded, they're very isoclinal. So that means up and down pretty well. But there's definitely a different sort of fabrics going on here. So that means different types of structures and how fluids react. But also this area too, if you follow that, the area between the black and the blue lines, right at that yellow dot, bifurcation point, go watch the shadow video on our YouTube channel. Love bifurcation points right here on Hook. And look at that. You're right within target area 1 and 2 radiometric areas. And this is, it's a great looking area. It looks absolutely fantastic. Remember these red lines, they'll come back in a few more slides. This is just generally showing the orientation of these two areas, just to show what the lithology actually happens. Tabular faults, huge part of the story, very huge part of the story. We need to move uranium fluids. Best way to do that is with faulting, because you got to move the rocks. So these are the tabular faults, all these north-south type of features. This big ellipse, remember that magnetic trend earlier on, how it bends north-south right at the Hook project, comes through here down to the S zone. Here's that magnetic trend. You can see it's a magnetic low within this ellipse. Everything to the eastern side, to the right-hand side of the ellipse are all magnetic highs. So there's definitely something going on here, specifically right in here, right where you have this really deep magnetic low trend. That looks like a whopping structure. That looks like something that has been moved time and time and time again. You take off the magnetics, now you can see the linears, you can see what they look like. They look like a network of, a structural network. One of my earlier videos, again, same thing, looking at the San Andreas fault. You get this type of pattern, and then you can start to see where mineralization can occur, especially at these intersection points. Look at that. Areas 6, 7, 8, intersection point. Areas 1 and 2. Areas 4 and 5 are towards below it, and the same with 3. They're at the intersection points. You throw these lines back on, we can relate that. We can relate this feature here, the structural component, that potential shearing and offsetting along the tabular faults north-south, and then you have the foliations, the lithology orientations following those red lines, and that is a geological feature that you can see at small scale, but nature being nature being fractal, and you can see repeating patterns at different scales. We're looking at SC fabrics, where the red lines that we just saw, those orientations are basically your slaty cleavage in this image down here. You start to put a force on that, you start to create these other lines, these other faults and fractures, and as you keep pressuring everything, you create this nice linear type of flow, being the lithology orientations that have been showing on these maps. And then you get these faults, these tabular faults, being these C-cell fabrics. This is fractal in nature. We see a lot of it in microscale, but you can take those same principles and apply them to Hook. So there's a good structural working relation to work with. So here we go, the red line on the magnetics, general trend of the lithologies in the area, and then the tabular fault, just a general representative. You throw them all over onto the model, not a absolutely perfect fit, but a very close fit. You see the different number of C-style faults happening within this model. You see them happening on Hook. Great idea. Look at the offsetting pattern too along the SC fabrics. Left side down, right side up. We'll see that pattern happen too. We saw these early July before the radiometric survey was done. 2 different rock styles here, 2 different lithologies, if you want to put it that. You can see the foliation here along the blue lines, and then we have a tabular style north-south feature cutting up through where Cameron is sitting down. So we know that these faults did exist. We know that these are real, and they look like they were active well before they were brittle, but that's where you want to see things remobilized. So when you think of remobilization, think of these north-south faults and how, as they continuously grind each other up and have fluids coming through, you're going to alter everything that's going on. So in this image here, where we're looking at that really strong north-south magnetic corridor, you can see that the lithologies, they change their direction, they bend, and that the direction of their trend can be attributed to the rocks and how they move. But we see that pattern, that same pattern from the SC fabric, left side down, right side up. That's the way the blocks are moving. When we jump on over to this side now, to the eastern side of the project, you can see in this close up here as well, the same movement picked up by the magnetics beautifully. Left side down, right side up. You got to think of the forces that go into moving these mass amounts of rocks, because this distance here between the top and bottom part of the ellipse is 1 kilometer. That's 1 kilometer of rock mass you are moving. And that's massive plates that you have to move. This is a big fault zone. This moves fluids. That's what you want to see. And you can see it down here too. 2 different offsets. You got a little chunk of it in the middle too. You can see that this fault is huge. San Andreas fault, have to move a lot. This is moving a lot. Draw in fluids. Put it all together. You put this whole CS style fabric idea, you're looking for cross structures because that's going to draw in the fluids the most. That is where you have the most porosity. It's very quickly. You just throw on these target areas like, hey, that's pretty cool. Let's look in there. Well, look at that. 1 and 2 lights up. South Geikie, area number 3 with Beckett. Areas 4 and 5, 8 and 6. Interesting. So radiometric anomalies are starting to correlate with magnetics as well. But magnetics is not the be all of what we've done up there too. We've also flown gravity. And the gravity survey, a little bit more coarse grained. This is a Rorschach test, I gotta admit. It's really hard to figure things out properly unless you have the magnetics to go with it. Once you take these magnetic layers over, you can start putting them over the gravity and starting to make sense of things that are going on. And this really applies nicely to South Geikie and Beckett target areas. Throw in the Taverners as well from the magnetics, just overlying. You can see that a lot of these north-south Taverner fault features show up as gravity lows. So we're picking up, we're seeing validation in our geophysical interpretations. Typically, you just want to follow gravity lows. You can pick out a ton of these little targets. And you say, okay, gravity low, gravity low, gravity low. But there are some meaning to a lot of these, and we'll look at that very soon here, especially for Beckett. And just for giggles, we throw on the cross structures from the magnetics as well, and you can still see gravity lows that are happening there. And the thing is with gravity, until you drill it, you never know what it is. Is it alteration? Is it a lithological gravity? So some lithologies are just naturally low in, just have a naturally lower density. Things like quartzites. Quartzites are just less dense than everything else. They could be they could be topographic. Sandhills. Sandhill would definitely show up as a gravity low. So you never know until you drill. And you put all of this together, and it's a mess. It's a busy slide. There's no doubt about it. And how do you start picking things out? Well, that's why you guys entrust us. That's why, you put your complete trust in us that we know what we're doing. And this is us showing you exactly what we're doing. There's a lot of interesting things to look at in Hook. A lot of our focus has been in South Geikie and also Beckett. These 2 targets are our priority areas right now. We are also looking at the other target areas as well, the radiometric target areas, but we have to prospect there first. We've got a basic understanding of what we think is going on up there, but we really need that geology to just back everything up and support what we're seeing geophysically. And that's what we're fortunate enough to do at Beckett as well. So with the field crew out there, hopefully we'll have some news coming out South Geikie after 2 weeks when the program is done. But you can see when we zoom in here that it's still clustered, but it's still a little bit more spread out. And this is where I invite you to come back and remember, number one, this is a big trend. This is a very big trend, 3.5 kilometers between this cluster. But in the circle, the diameter of the circle, number one, is 2 kilometers. And you can see that they're on multiple trends here. There seems to be some sort of I guess, similarity or overlapping with the surface feature, the radiometric surface feature with the lower magnetics. That, again, supports a lot of the case that what we could be seeing here are outcrops. And there's gaps in the data because, again, remember the overburden. You don't need a lot of overburden. This is northern Saskatchewan. There's a lot of overburden. So you're going to have gaps between these trends. But you can make out some of these trends already. And with these thick red lines, if we can start to follow up, if there's overburden between some of these anomaly areas, we have to see what's through them. What if the trends continue like this? What if the trends are a lot longer and we just can't see them because they're under the overburden? There's a lot of potential here. Throw in the gravity. Let's explain some of these gravity targets. So we have a nice long one here, kind of follows the orientation of the lithology. Still a very interesting area. We have this anomaly here that follows our radiometric trend and starts to, and then the density changes once you really cross that black line, which is the Tavener fault. Another small anomaly along trend, and then we have this other anomaly that occurs really along the Tavener and at that cross structure of a lithology. So a very interesting area. When you throw it back into the magnetics, you can see that gravity anomaly 1 really does follow a magnetic signal, as does gravity 2, especially along that contact with the magnetic high. That is a great place to really get some geological information and following up with mineralization, because mineralization doesn't matter really what kind. They love contacts. And if this is a geological contact, mineralization loves contacts. So great, definitely a great area that we want to follow up on. And then this other anomaly down here, it looks like a magnetic low as well. So what's really happening? When you look at the magnetics in this area, I've just drawn on a yellow line, might be hard to see. Take your eyes a few minutes to see it in the bottom right-hand corner of the image. Everything to the southeast of there, to the bottom right, is all a magnetic high, regardless of what side of the Tavener, that black line fault, that you're on. West side, east side of it, it's all a magnetic high. However, you still see that the same magnetic signal over here on the eastern side, but over here on the western side, there's a huge magnetic low. Your magnetic signal goes from high to low right at that Tavener fault contact. This is one of the ideas. If this is of the same rock type, but something has changed, its geophysical parameters, its chemical parameters, something has happened to that rock. There's a structure in the area. What are the chances that that structure has had to do with mineralization? It is part of that north-south structure that goes up, that we can trace through the magnetics all the way up to McArthur River. Is this a high-grade structure? And we've got South Geikie right here with radiometric anomalies. What's beneath the surface there? We're going to look at Beckett. That was an exciting place to leave South Geikie, but we got to shift to Beckett. Going to focus on this mafic gneiss lithology right at that contact. You can see on this image right away that magnetic high to the southeast, lesser magnetics to the northwest, and we'll get on that. That mafic gneiss, we did map it earlier July. It's basically a mafic gneiss with granites, and then everything else that was mapped northwest of there, semi-politic gneiss. So absolutely great place. What does this mafic granite rock type of look like? Mafic, they're the greener rocks, and the granites are the white rocks. And you can see how they're basically together. And in this image, once you get your eyes kind of attuned, you can see that it's a wonderful jumbled mess, a ladder almost of mafic granite, granite mafic, and so forth. Interesting rocks. What does that have to do with anything? Let's go down to S zone. We haven't talked about S zone in a while. We've seen it in all those maps, but what does it have to do? Earlier on, talking about Charles Beaudry, this map is from a 1980 report that Charles Beaudry co-authored. Look at the rock types that they're describing. The red is the S zone. It's about 10, 20 meters long, and it's in close contact with this mafic gneiss, up to 65% U3O8 uranium vein right there in contact or near contact within 20 meters of a mafic gneiss. So that combination, that being able to trace that particular lithology or group of lithologies, regardless, it's a magnetic feature that we can follow that links the two as well. The lithologies seem continuous. It seems like seems like the trend continues there. Where else have we seen mafic mineralization? Let's look at the PLS trend, Arrow and Triple R. We're over here at Hook. We're going to jump over here to the southwest corner of the Athabasca Basin, the PLS trend. Arrow deposit on the left, Triple R deposit on the right. Red is mineralization in both cases, mafic gneiss mixed with granites. Purple, not so much on Triple R mixed with granite, sorry, but it's still mafic gneiss. Look where the mineralization is close to the mafic gneiss in this area. Yeah, graphitic shears, but you don't necessarily need graphite in all of your deposits. And then semi-politic gneiss, it's the same rock types we're seeing at Beckett. It's the same rock types. Proximity to mineralization, mafic gneiss. What are the chances that there is a certain lithological control on mineralization along with structural control. We've got the right setting here. We've got the right setting at Beckett on our Hook project. And there it is. You can follow that zone down. So that zone is very exciting. Remember what I mentioned about the magnetics? The magnetic to the southeast of that purple line is all magnetic high. To the northwest, it's all lesser magnetic high. But if you follow that trend down right into this area, you can see that there is a magnetic low. Similar to what we're thinking about South Geikie, that change in that magnetic low, especially associated with structure, may have had hydrothermal alteration that could have changed the mineral properties of the rock, so therefore being altered, and thereby changing the magnetic quality of the rock as well. So that's how we're using magnetics to also look for alteration. We're seeing the blues here. What does this mean? Right along contact. Here we are zooming in close to Beckett. A magnetic low, 4 kilometer long trend. That's a pretty decent trend. Seems to be right in close contact with that mafic gneiss area. And there's the gravity in the background too. It's a gravity low. And we're going to really focus on the gravity now for a bit, because I think this whole trend here just really lights up nicely in the gravity and can be explained, especially this anomaly right in the middle of here. If you notice that radiometric trend kind of going right up into it as well. There are 2 blue lines now. And again, they're both produced from the magnetics, but I just copied one over and kind of highlighted a valley here, a magnetic low valley, and I isolate the rocks between these 2 thick layers. And now we're looking between the 2 blue lines. So it looks like this is one of those lithological corridors that is defined by rock units manifest as a gravity low. So they're just a lower density rock. Maybe it's a quartzite. Maybe it's some sort of pegmatite. Let's get rid of that corridor and let's look at this corridor, because if you go from red arrow to red arrow, it looks like this corridor should be a gravity high. That's its rock properties. That's its background. But look at this area right by the Taberner Fault. Taberner Fault are those 2 north-south black lines. There's a beautiful gravity low there, and you can kind of make out some orientations happening in there. Is that what we're seeing? Gravity high being fresh rock and gravity low being altered rock, structures and fluids. We've got magnetic lows happening, but we've also got gravity lows happening. It's a beautiful mixture of geophysical properties looking for alteration. Let's look at another deposit to compare with Beckett. So here we are at Hook, Raven-Horseshoe. Let's go look at UEX's Raven-Horseshoe. I had a fun tendency for that project. Basement hosted mineralization, Raven-Horseshoe, over 30 million pounds. It's a nice little deposit. What does Raven-Horseshoe have to do with Beckett? Well, let's take a look. Taberner faults, first thing I'll point out. The black lines that you can see north-south. There's 2 on Beckett, there's 1 on Raven-Horseshoe. White arrows that I've just drawn in, showing gravity highs on both ends of a gravity low. And this is a regional gravity low. I have to point out both of those images are to scale. The black line that you see in the bottom left of both of those pictures, that's the scale bar. It's over a kilometer, but that is the scale between these 2 images. You can pick up these gravity low trends that are in these orientations. There's a multiple, they're repeating patterns. So there are multiple of these parallel features, but in both cases, they're following the lithology orientation. They're following the lithology, the way the rocks are all placed down. And then there are these cross structures that you can also pick up in here as well with the orange lines, which in the Raven-Horseshoe case controls mineralization. What's happening over at Beckett? What does that structure, if it is a structure, have anything to do with the potential for mineralization? Let's hope it has a lot. The similarities between Beckett and Raven-Horseshoe are very striking. Gravity low feature emanating out from a Taberner fault. Raven-Horseshoe, the idea there is that these Taberner faults supplied the uranium for mineralization. You can see fresh rock on the outside of the gravity low, and once you're within the deposit itself and drilling it, it's altered, it's clay altered, the mineralogy is altered. You've added uranium to it, you've taken away other metals from it. It's altered, it's changed, it's softer basically, and you've got structures coming in there because you need to move the fluids in there, so you need the structures. It's wonderful. Beckett is an absolutely exciting target. All of these targets, Hook is a wonderful looking project, and for us starting out with 2,500 meters, trying to get into more than 2 or 3 areas, it's not worth it. We want to put the focus into a couple areas, which is why we focused on South Geikie and Beckett. It's have those have what we need to see, and the distances in some of those areas, 2 kilometer strike lengths, 3.5 kilometer strike length of trends to follow up on. That's not small, especially with a drill. If you're drilling 400-meter spacing, there goes your budget almost just in one area. So we have to be much more discreet and focused into our areas. Putting at least 4 holes into each area provides us a very simplistic look into the geology that we need to understand to see the potential for mineralization there. And based on the geophysics that we're seeing, we think they're quite exciting. So now with the prospecting crew that we have up there, they're ground truthing some of these radiometric anomalies. Are they boulders? Are they outcrops? If they're outcrops, what are we going to learn from them? Even if they're boulders, what are we going to learn from there? Can we trace it back to their source? What are these? What kind of grades are we seeing? What are the reds? But we've got the prospecting crew out there now. Like I said, 2 weeks time, we will be releasing our results, our preliminary results from what we have identified in these areas. South Geikie, this is the radiometric, those surface anomalies that exist there. Very, very excited to be able to expand on that and learn from that. And what is causing that magnetic low? It's such a cool feature with the structure coming right through there. It's very exciting. Something has changed those rocks. Beckett has great similarities with the PLS trend, with the Raven-Horseshoe deposit. That's just only a few. And guess what? Those are all basement hosted deposits. They're all basement hosted deposits. So you can kind of assume, or at least hypothesize, that the way we explain these things are very possible. We're not saying that these zones are going to have mineralization, that we're looking at a deposit. We're just saying that from what we have examined, what we've just shown here, they've got a great chance. They got a wonderful chance. And then target areas 4 to 8. This is just going to keep adding to Hook. And you've seen the terrain up there. There's a lot of anomalies that we probably haven't found. So that's when we go back to geology, and that's when we go back to looking at the geophysics and everything, and then just seeing how everything we have seen, what we've accomplished with this first pass drill program, which is scheduled to start in the next 2 weeks, is very exciting. We're just going to build on this, but the potential for mineralization is definitely there on Hook, and we're really hoping that we can prove that it's there for sure. So a big thank you for staying tuned and watching this whole thing. I hope I have you excited about Hook. Hope you understand where we're coming from, why we're trying to focus on these 2 areas. We've got limited program, but we don't want to go too hard into this right now. These 2 areas alone need probably 2,500 meters each. So these are excellent areas to start looking into, and we're going to really pound out Hook. Thank you very much. Stay safe, stay healthy.